has trig in it, so it's a little bit different. Remember, I told you guys that I chose different examples to put in these notes that kind of expose you to all the different types of common related rates problems. So the tracking a rocket example. I started to draw a little picture here. Remember, I said it's always helpful to draw a picture whenever you can. The question says, a spy uses a telescope to track a rocket launched vertically from a launching pad 6 kilometers away. So in my picture, I have the guy with the spy with his telescope, and then the rocket has been launched, right? We'll say that this was the launching pad, and the rocket is launched and going up, up, up. At a certain moment, the angle theta between the telescope and the ground is equal to pi over 3, and that's in radians, and is changing at a rate of 0.9 radians per minute. So we're going to call the angle between the ground and the telescope theta. And we're given the rate at which theta is changing, but we're going to be solving for another rate at the moment that theta is equal to pi over 3. So theta being equal to pi over 3 is describing the moment in time that we are solving for this other rate, which I haven't gotten to yet in reading the question. Now, as the rocket is going up, 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 maybe I should fix this so that we'll say it's like looking at the tip of the rocket. Oops, I accidentally erased some of my rocket and some of my telescope. Okay, so let's say, there we go. The telescope is following the very top of the rocket. Or pick one part of the rocket or the whole rocket, I don't know. But as the rocket travels up, 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 the telescope is going to end up angling up, up, up to follow it. So theta is actually going to be getting bigger and bigger as time is passing. And we're given that theta is going to be changing at a rate of 0.9 radians per minute. We want to know what is the rocket's velocity at that moment. So going back to my picture, I want to finish labeling my picture before I state the given rate and the rate that we're solving for, so that then I can come up with the relationship between the quantities that are changing that I care about. As time is passing, the rocket is going up, up, up. So it's getting higher and higher off the ground. So I'm going to call the distance between the top of the rocket and the ground, I'm going to call that y. You could use any variable you want. I'm just going to use y. And then the distance between the rocket and the telescope is also going to be increasing as time is passing. And I can call that, I don't know, I'm going to call that z, that quantity z. Okay, so as the rocket's launched, if you were to start a stopwatch, time's passing, the rocket would be going into the air, so its height off the ground would be increasing. The distance between the telescope and the rocket would be increasing, and the angle between the ground and the telescope would also be increasing. Does everyone understand this situation and the picture that I have drawn? Are we all okay with that? Okay, I'll take your silence as you're all good. Okay, so now let's go back to the steps that we normally follow for these related rates problems. So the rate that we are given is the rate at which the angle is changing. So the rate at which theta is changing. So I'm going to say we're given d theta over dt. And since as time is passing, theta will be increasing. I'm saying that d theta over dt is equal to positive 0.9 radians per minute, which I'm going to abbreviate as rad per minute. We are trying to find the rocket's velocity. So how fast the rocket is traveling with respect to time. And its direction, right? Velocity is a vector quantity. It has both magnitude and direction. So to describe the velocity, I'm going to use y, how fast y is changing with respect to time. How fast y is increasing with respect to time, because we know y is going to be increasing. So I'm going to let velocity be represented by dy over dt. So we are trying to find dy over dt when theta is equal to pi over 3. So at the moment that the angle between the telescope and the ground is pi over 3, that's the moment we want to know the rocket's instantaneous rate of change, or its velocity. So we've stated the given rate, the rate we're trying to solve for. We need a relationship between the quantities that are changing that we care about. And I already talked about how we have 3 different quantities that are actually changing, and they're labeled in this picture. The thing is, we need to come up with an equation that has theta in it and has y in it. And that's because we are given d theta over dt, and we are being asked to find dy over dt. We are not given any information about z or the rate at which z is changing. And you probably noticed that this picture kind of creates, in the quantities, so z and y changing, it creates a right triangle. So if you think back to right triangle trig, that's when you were using SOHCAHTOA. Okay, we want an equation that will have theta and y. So theta and y. So that's the angle, and then the side opposite the angle. Well, I also am given the side that's adjacent to the angle. So using tangent for this problem to relate y and theta is going to work. Tangent of theta is equal to opposite, which is y, over adjacent 6. And you can leave the equation as is, or because we know we're solving for dy over dt, it might be easier to just multiply by 6 on each side. So rewrite this as 6 times tan theta equals to y. So before I differentiate, does anyone have any questions about any part of this?
Could you repeat why you use SOHCAHTOA, or what you're talking about right there? Sorry.
Yes, okay. So looking at the rate that we're given and the rate that we're trying to find, we know that we need to come up with an equation that has a theta in it and a y in it, so that when we differentiate with respect to t, we end up with a d theta over dt and a dy over dt. Looking at the picture and thinking about how we could come up, like what is the relationship between theta and y, or how we could come up with a relationship between theta and y. You just notice that this situation kind of creates a right triangle, right? Where this would be the right angle. Now, we don't want to have an equation that has z in it, So like Pythagorean theorem is out, right? It's a right triangle, and you probably recognize that. And I know whenever you guys see right triangles, you're like, Pythagorean theorem. But if we have an equation with z in it, we'll end up with a dz over dt, and we don't know what that is. And if we use Pythagorean theorem, we wouldn't have theta in our equation. So then well, now going forward, you'd think, okay, well, since theta is involved, I'm going to be using my right triangle trig, SOHCAHTOA. And because we want an equation that has y and theta, since y is opposite theta, and we are given the side adjacent to theta, and that's not changing, so we're able to actually plug that value in. Before we differentiate, we can plug the 6 in. We are able to come up with the tan theta equals to y over 6 in order to relate theta and y. Did that help, Drew?
Yeah, thanks.
Okay. So I multiplied by 6 on each side. You could leave as it was originally written, or you could do what I did. And now I'm going to differentiate with respect to t. So I'll pull out the 6. The 6 will be there. And to differentiate tan theta, we have to think chain rule, where tangent is the outside function, theta is the inside. So derivative of tangent, you guys all know, is secant squared. I will leave the inside alone, the theta, and then multiply by the derivative of the inside with respect to t, which would be d theta over dt. And then the right-hand side just becomes dy over dt, since that's just the derivative of y with respect to t. Once we've differentiated, we're ready to see what we can plug in, and if we're ready to then solve for the rate that we're trying to solve for. So I can plug in 0.9 for d theta over dt. And I can plug in pi over 3 for theta. So 6, I'm going to flip this around actually so that I have dy over dt equals on the left, and then 6 times secant squared of pi over 3 times 0.9. Now I am okay. You can use the unit circle to figure out what secant of pi over 3 is. You can also, and then square it, you can also use your calculator if you want. So either way. And I'll take the approximation. Actually, give me just 1 second. I just want to confirm that the answer I have in my notes is correct. Yeah. Okay, so using the fact, no matter what, you can't type secant into your calculator. There's no secant button. But if you remember, secant is the reciprocal of cosine. So we could actually rewrite the secant squared of pi over 3 as 1 over cosine squared of pi over 3. And if you do remember your unit circle and you remember that cosine of pi over 3 is 1/2, so it's reciprocal would be 2. And then when you square the reciprocal, that would be equal to 4. You could do that, or you could type it into your calculator. So if you wanted to rewrite this so that you could just type everything into your calculator, you could rewrite this as 6 times 1 over. I'm going to change this to be cosine of pi over 3 squared, written like that, because that's how you would have to type it into your calculator. So what is that? 21.6. And since y, the unit is kilometers, right? Distance is being measured in kilometers. Time is being measured in minutes. The units will be kilometers per minute. So to summarize, we could say the velocity of the rocket is 21.6 kilometers per minute when theta is equal to pi over 3. So you could use to come up with the 21.6. You could either evaluate cosine of pi over 3 using your knowledge of the unit circle. I also am okay if you just want to type that all into your calculator. Does anyone have any questions? Okay, Miss.